Hello, and welcome to Data Workup for TA Instruments Q series. So this section, the first section of this video is going to be applied to both DSC and TGA, and I suppose also DMA data workup. So I'm not going to be too specific on instrument model just because we're going to be able to use this one software to analyze all the different data types from the different instruments. So I'm going to go over how to download and install the software. You're going to want to go open a web browser and search for TA Instruments software. And then it should be the first link, software downloads from tainstruments.com. Opening that page, we are going to go down to the Advantage/UA software and download this. So this is actually quite a large file. It's 850 megabytes, and we're going to fast forward through the download, but you don't actually need to install the whole thing. All right, once this is downloaded, we're going to run the installer. It may ask for administrative privileges. You will need to be able to have admin, so you can't install this on school PCs because you likely don't have administrative privileges, but you can install this on your personal PCs. It's free. A lot of school PCs, the lab ones especially, have the computer labs in the science buildings usually have this already installed. So when we actually get to the installer here in a second, we're not going to install the entire software because this includes all of the instrument control software and everything, so we don't need that, and that'll make the installation much smaller, and you don't need a whole thing of several gigabytes. So we're going to hit next, accept the agreement. Technically we should read that. Give it a name or put in your username, and then hit next. And then instead of the complete, this is where we're actually going to choose the custom installation. If you do complete, it will install the instrument control software, which you likely don't need. So in this case, we only want to select universal analysis. You can install the help files, but again, it's the help files for all the software. So that's over 400 megabytes, whereas the analysis software is only 22.5 megabytes. So we'll hit next again, and it's going to do the installation. It pops up with this error saying that we couldn't start the instrument control software, and that's because we didn't install it. So we can ignore that and hit finish. And then it put an icon on the desktop, so we can use that to open the software. So TA Universal Analysis is the software that we are using. To open a file, it's very simple, file open. This is all pretty standard stuff. On my desktop, I put those two files that we collected for the TGA. This next section I'm going to talk about is still applicable to any file type because I'm going to show you how to export the data first, and then we'll go into more specific data analysis. So we're going to open the gypsum one first. It gives you this option, you can change, or this dialog box, and you can change options such as what signals are displayed and stuff. That's more useful for some other data file types, but the defaults for TGA are usually okay. So within this window, you can have multiple little windows, but I'm going to expand it since we only have one. So if we want to export the data to like Excel or Origin or something, we go up to File, and we're going to export the data file. So file and plot so file signals, plot signals, and then file and plot. So if you did any math, such as taking a derivative or something, that's going to be a plot signal. File signals only include the weight percent and the mass and the temperature. So if you want to actually extract like the derivative plot, then you need to choose plot or file and plot. Usually I just do file and plot because I'll decide what data I want to use later. And then you get to choose what output signals you actually take. So you don't really need the balance purge and the sample purge flow rates, but it does record them for the entire run, and this includes all the different instrument types. Um, and then for the output format, the default text file is perfectly good for opening in Origin or Excel, but some people prefer like an ASCII or something like that. And then for the character set, leaving it in Unicode is going to be just all around compatible with things. And then in the options, there's usually, you don't need to choose anything from here. But if you want a data file that's just data, so at the top of the data file, there will be what's called the parameter block, and it's just all the information that's built into, that's collected from the instrument. So it'll have instrument model, it'll have, starting mass, it'll have info about the run parameters such as ramp rate and settings like that. So if you want a data file that just has the data and no information at the top, which might work better for some programs that you want to use, then you'll select that option. Um, some data has breaks or flags, such as DSC. So DSC has end of run markers. So once you do like a heat, it'll have a marker for end of run, and then you do a cool, it'll have a marker for the end of that run too, so that you can break up the data. If you want a continuous data set, then you'll choose no data breaks or flags. The no invalid data points, that one I've never really had a reason to do. I've exported tons of data and I've never really had any invalid data. I suppose you could select that just to be safe, but again, never had a problem with it. So we'll hit finish here and it'll ask us where we want to save it. And reminder, this one was a text file. So I'll save this on the desktop and then the window disappears. And if we go to the desktop, we now have gypsum.txt, and we can open that in Notepad. And this up here is the parameter block that I was talking about. So if you don't want that and you just want data, then you could select that option and it'll remove that. So this gives you information about your instrument. So what mode you ran in, what model it is, serial number, who's the operator. This is where you can view comments that you made in your run. It tells you even where the file was saved, the size of the sample. So it gives you tons of information. And then it tells you what gases you're running, what the pan type is, the purge settings. And then this part can be a little confusing at first, is because there are 5 columns here and none of them have headers, so you don't necessarily know which one's which, but actually they're up here. So it says number of signals, 5, and then it has signals 1 through 5 listed out. So the first signal, the first column is time, the second column is temperature, the third column's mass in milligrams, and then we have our purge flows for the balance and sample. So this one actually exports just the mass. It doesn't export weight percent. It's easy enough for you to calculate weight percent on your own in Excel or Origin or something after the fact. So if we open Excel, sorry, it's opening on my second screen, which is not visible. If we open Excel and open a blank workbook, we could either drag and drop this. So we could go to the desktop and we could drag and drop the txt file in and it'll open like this, or we can go file open and select it from there. The columns are already each of the signals is already in their own column, which is really handy because some data types you have to split out, but this one automatically splits them. And then if you wanted, you could do a copy and then transpose and get the headers on top of each column if you wanted. That's usually the simplest way to do that. And then you can go about manipulating your data and plotting it in Excel if that is your choice. So I'm going to close this without saving it. This was just an example of how to open the data in Excel. And we will go back to our universal analysis software. So another thing that's universal to the different instrument types is how to export a PDF of this. So you can just go to File and hit Export PDF, and this will export. I'm going to take out this period in here because Windows doesn't tend to like extra periods inside of file names. So this will just export a PDF of exactly what you see. So if you have annotation on your plot, it'll export the annotation as well. One thing that it exports that you don't see on your universal analysis, so up here there's no header. I mean, there is, but it's not as detailed as this one. So this one has a more detailed header, but then it exports exactly what you see. So if you had annotations on here, such as mass percents and stuff like that, and weight changes, it would export those as well into the PDF. So this is a handy way to get a quick export of the plot. Now, this isn't replottable in another software, but it's nice to be able to look at it without having the universal analysis installed. If you're emailing it to someone and they don't have universal analysis, it's nice to have something quick to look at, such as that. Now we're going to look at DSC specific data. So you've already seen how to install universal analysis and open files. So on my desktop here, I have the PET as is that we collected and the PET quenched files that we collected. So these are available for download if you want to follow along. It should be in the description. There should be a link that you can use to grab these files. So I'm going to go to the desktop where I have them saved, and you can hold Control or Shift and highlight both and open them both at the same time. So I'd say that we should look at the as is sample first, and I'm going to maximize that. A couple handy tricks for DSC in general, not specific to this data, are right-clicking directly on the line. So if we right-click on this line, we'll get different options than if we right-click in the empty space behind it. So if we right-click on this line, we can hit Hide Curve or Analysis Curve. Those two are very helpful. So if we don't want to see this, we'll hit Hide. And if we want to see this as the only one, we'll hit Analysis. So if we hit Analysis, it grays out the other two curves. So if you remember what our program is, it was a heat, cool, heat from near room temperature to 275 and back to room temperature. And then the last heat was back to 275. So this, the fact that this one starts separately and this heat starts from near the cool section indicates that this was the first curve. So this was the first heat. As it goes along, you can see a slight glass transition that's not very well defined. And then there's not this peak that shows up in gray back here. And then it has these two melting peaks. So remember that with DSC, you have to indicate which direction is exothermic or endothermic in your plot because there's different conventions. So exothermic is up in our plots, so this endothermic peak here is likely a melt. And we know that from just looking at the thermal properties of PET that it melts somewhere around 250 to 260. It really depends on the chain length and additives that could be in it for if it's higher or lower. But this one had two peaks for the melt. And then if we right click back on, so if you right click on a grayed out one, it won't give you the same options. Now when we right click on the green one, we, instead of getting analysis curve, we get full range as the option. So that will bring us back to seeing all the data. You can also go full range from the top left. There's the red one here that's full scale all. So if we right click and hit analysis curve, then when we full scale all, full range data limits, the other red one, then we will get all our data to be visible again. So there's a reason that we do two heats on DSCs. As you can see, there's quite a difference between the first and second heat. The first heat we typically think of as containing information about the thermal history of the material. Now, it's not going to give you an exact outline. It's not going to give you some sort of like roadmap of where this material has been and what it's dealt with in its lifetime, but it will tell you if it's different from the native properties of the material. So the second heat, we would consider the native properties of the material because it's been heat cycled, melted, and cooled back down. So now it should be in its most native form, whereas the first heat was greatly affected by how the material had been stored or used, or even like if it had mechanical stress or thermal stress put on it, it'll look a bit different. So the fact that we don't get this exothermic peak here between the glass transition and the melt in the first one indicates that the sample is highly, highly crystalline. So this peak, exothermic peak in the second heat, is what's called a cold crystallization. So that's where the sample is a bit amorphous or fully amorphous, it depends. In this case, I'm going to say it's partially amorphous, and it can reorganize itself a bit after it's heated up enough past the glass transition, and so then it will release some energy getting into a more ordered state. And so a sample that shows cold crystallization is at least partially amorphous, and a sample that shows none, as in the first heat, is very crystalline. The high crystallinity of the first heat may be part of the reason that we see two different peaks on this melt. I've ran this PET sample dozens of times for classes, and sometimes there's two peaks, sometimes there's not. I think it has to do with a sample being in a very ordered. If it's in a very ordered state, it'll be a little more likely to melt a little earlier. So this one melts a little earlier than the bulk of the material. If we look at, I missed the plot or the line. If we look at the cooling curve now, so let's make this our analysis curve, you're going to see that there's this difference. The heating curves are down below zero, whereas the cooling curve is above zero. And that's normal. There's usually this big block of empty space in between. That has to do with flux in or out of the system. So on the heat, we were doing flux into the system, and on the cool, we're doing flux out of the system. So there's going to be an overall constant amount of heat flow that's related to the flux in or out of the system. So this little hook down here, we call the turnaround hook. There's a startup hook on our first heat, the turnaround hook again on the heat to cool transition. And that's just because we're establishing a new heating rate. So I've mentioned that heat flow in and out of the system is very important to the calculation. Sorry, heat flux is very important to the calculation of heat flow. And so when we go to change from a constant heating rate to a constant cool, then there's going to be some fluctuations. And we don't include that in, we don't assume that's like a melt peak or anything. Sometimes these are much larger, and you might be tempted to think that they're a melt peak. If you see a well-defined melt peak like we have here, then you have no reason to think it's a melt peak. But if you don't, and you see no melt peak, but you see this huge hook and you're wondering if it is a melt, then you should maybe do another run where you expand the range. And if it was just a turnaround hook, then you'll see it at the end of the heat regardless. But if it was a melt, then you should hopefully define it better. And then, so as we go back down on the cooling, so our sample is now melted. And so as it cools, it will crystallize. So this crystallization is quite broad. And that's just because it's crystallizing relatively quickly, and we're on a fast ramp. So it's kind of spread out because we're on a fast cooling rate. So we have 20 degrees a minute of cooling rate, that it kind of spreads out that crystallization peak. And then we have our glass transition over here as well in the reverse, or while we're cooling, because it's a reversible transition. You can use that glass transition temperature as opposed to the one for the heat, but most of the time people will report the one for the heating. So I'm going to go back to full range. And we're going to look at the second heat because we want more of the native parameters of this uh, polymer. So if we go up to the Analyze dropdown, this is where you're going to choose your analysis for the plot. And they're very well labeled, such as glass transition is labeled very well because that's what we want to look at. It can be easy to zoom in on that. So you draw a box and click inside the box and zoom in, and it's a bit easier to get your baselines. For a glass transition, you want to try and choose points that are at the plateau before and after. And so this can be difficult, especially looking at our plot right now. When we were zoomed out, it looked relatively flat, and when we zoom in, it looks slanted because it is. So it can be a little trickier to choose what the plateau is before and after. So if I choose glass transition, I'll get these two red crosshairs at the far ends, and you can drag them by clicking on them. Or what I like to do personally is double click and it moves them for you. So I'm going to double click. This plateau on the bottom side is pretty easy to identify. The plateau on the top side, if we try and draw like a tangent line to the curve, it looks like the plateau starts somewhere around this point. And so when we hit enter here, which we will use to accept our changes, you'll see the lines that it's drawing for the plateaus. So if this upper line doesn't look right, you might delete this result and try again. The bottom line looks pretty good to me. They both look pretty good, so I think we would accept this. One thing that throws people off sometimes is this little like dip down below. This isn't inherent to a glass transition. This is what's called enthalpic recovery. If you want more information about it, you should do some research. It's a pretty complicated process that we won't get into here, but it can throw people off when talking about or when trying to choose the analysis points for your glass transition. Now, glass transitions are a range, so when you report them, you typically are going to report the range. So for this polymer, we would report 76.89 to 81.51 degrees. And if you wanted more accurate results, you'd probably run the sample in triplicate and then average the start and end temperatures for your glass transition. You can move these numbers around however you like. If it makes the plot easier to read or anything like that, that's up to you. You will still get these little after images of the text. That's not going to affect anything. It's just a display thing. If we hit full range again, now it looks like we should move them into a different location because of the different scale. So that's a little different there. For other transitions, such as the cold crystallization or the melt peak, there's different ways you might analyze those. So you could choose peak maximum, and you'll get the same red crosshairs, and you'll want to choose left to the left and right of your peak and hit enter again, and it'll give you a single value. You might want to choose the integral, so you might want to integrate the peak. When you integrate the peak, you have the choice of what type of background you want to use. Most of the time, a linear one's going to be good unless you have a really slanted background, then you might want to try a different one. So I'm going to choose the linear background. Now, I'm going to hit escape here, sorry, and we're going to zoom in because it's going to help us. So draw the box and click inside. Now we're going to choose the integrate linear. And when you look at this peak, the plateau is somewhere right about here. So we're going to double click there. On the other side, the plateau is a little harder to define because it starts going towards the melt peak. And so I'm going to choose a point here that I think is good and then hit enter. And it's going to not only give us the peak maximum, which we had previously done, it's going to give us the integral for the peak. So if I right click on one of these peak maximum values, I can hit delete, and I happen to choose the one for the integral, so I chose the wrong one. But one thing that I'll show you right now is we're going to right click on the plot, and this will help you with the integral. That's why I'm showing you now. And we're going to hit signals. And on Y2, we're going to choose heat flow, but instead of normal, we're going to choose derivative with respect to temperature. And then you'll be able to see the derivative values in blue. And if we try second derivative with respect to temperature, you can also see those if you want. So the derivative values can help you with finding where the inflection points are. There also is a logarithmic derivative option as well. So if we zoom in on this region, unfortunately, it's a little tricky on the second y-axis to tell where the inflection points are. So what you can do is you can right click on the plot and you can choose a manual rescale. And so for Y2, it looks like we want to get in the range of minus 0.2 to positive 0.2. So I'm going to change Y2 to minus 0.2 to positive 0.2 and see if that helps. It looks like that might not have been enough, so I'm going to try again from minus 0.1 to positive 0.1. And then I'm going to have my labels of minus or of 0.05 to see what that gets us. So it's a little noisy, and I'm going to right click and choose our analysis curve again because it also does it for the derivative. So now here with this integral, we can choose the point at which this side's flat, and then over here we'll choose the point at which this side becomes flat, and that'll give us a more accurate integral for a peak that doesn't have very clearly defined plateaus on each side. So this gives us our integrated value of 19.13 joules per gram. It's always normalized to the mass because more mass equals more signal, or less mass equals less signal. So now I can go full range all again, and you can see that we might have to rearrange some stuff if we want this to make sense as to what plot is going to what. The integral isn't very useful for the melting point, so I'm going to take that off. Again, right click, go to signals, and then Y2 is going to be changed to not used. For the melt point, we typically do what's called the onset. So I'm going to zoom in on the melt peaks down here, and we're going to choose the second heat. Again, we want the native information about the polymer, or the information about the native polymer. And so if we go to analyze, we have onset point. And so we get two crosshairs again. And so we'll choose a spot where this plateaus, and we'll choose a spot where the slope of this downward peak, this downward line in the peak, is relatively constant before it starts to inflect, right about here. And then we're going to hit enter, and you'll see it draws tangent lines to determine the onset point. So this would be the reported value for a melt peak. Ideally, your melt peak would be a lot sharper than this, but it can be tricky with polymers because they can have wide distributions of polymer chain lengths, or there can be additives and stuff that are trying to shift these. But this is typically what's reported for melt. So we've shown you how to do our glass transition and how to integrate peaks. You can integrate peaks that are in the endothermic or exothermic direction. And if you do peak max, it works for peaks going in the endothermic direction, so it might be counterintuitive. So if we choose both sides of this peak and hit enter, it's not going to go only in the positive direction, it will also go in the negative direction. So I'm going to delete that result just because that was just an example. So this would be an example of a plot that you might export, or a view that you might export into a PDF that gives you the information about your polymer. So it'll give you information about the glass transition and the melting onset. Integrating the cold crystallization peak is not exactly information that anyone wants to know by itself, but if we choose the quenched value, the quenched plot. So this is our PET that was quenched. So we melted it on a hot plate and then we cooled it down really rapidly so that it should be all amorphous. So that means if we select our first curve, our first heat has this huge cold crystallization. That indicates that, or no, sorry, that is showing the amount of amorphous content, which we are assuming to be fully amorphous because we did the melt and quench ourselves. So what we can do is analyze this for the integral. I'm going to, skip around here. I'm going to plot the derivative as we did before, so I can try and get an accurate integral here. Zooming in, it's a little easier to see this integral plot for some reason. It's always different. So we're going to make that our analysis curve, and then we're going to choose the integral and choose the plateau on the left side, right where it starts to plateau, and on the right side, right where it starts to plateau, and then hit enter, and we will get our integral value for what we presume to be fully amorphous. And so what we can do with this information is we can take the ratios of these to determine the percent crystallinity of the native polymer. So this second heat is showing us what the polymer, or how the polymer likes to arrange itself when it's allowed to melt and fully cool without being stressed thermally or physically. And so at 19.13 joules per gram, we can then do some simple math. 19.13 joules per gram divided by the total. So you would think you might add the two together for the denominator, but we're assuming that the 34.31 is the 100% amorphous value. And so we would get a little over 55, almost 56% amorphous content for the native polymer as is, like unstressed. So this polymer has been sitting in the drawer or container for however long. So again, we're using the second heat on the as is polymer. And so we can get rid of our derivative. And we would also note the glass transition and the melting point onsets for this as well. It gives us another data point because they shouldn't be too different between the two samples. And so those are the basic things for analyzing DSC. There are other things you can do with DSC, and we might make that another video for that, but this is the basic stuff that most classes will utilize and can get a lot of information about polymers from. So thanks for watching. Shoot me an email if you have any questions.